Thanks for having me, and thanks everyone for coming to here. I work for Electric Power Research Institute. We're a nonprofit for the public good, mainly funded by the electric utilities. And I want to talk today about ground bottom ash and concrete. And just before I get started in the talk, I can touch on that last question that we had about the environmental implications. I've not seen any studies about the use of ground bottom ash and concrete from an environmental perspective, but we do know that the composition of bottom ash tends to have less of the metals of concern compared to fly ash. So we'd expect that there would be lower environmental risks associated with using bottom ash. And we know that fly ash is really well accepted in use in concrete. In fact, the EPA has done a study reviewing the environmental implications of using fly ash in concrete, and it showed it was a safe material to use. So I think we could extrapolate from what we know about the composition of bottom ash and what we know about the behavior of fly ash in concrete to say we'd expect it to be safe, but I haven't seen any specific data on that. So with that, let's see. All right. So why are we here? And before I get too much further along, I'm not a material scientist, so I'm just not going to be able to present at the level of depth as some of the other people that presented before me. But instead, I'll try and talk about the perspective from what we're doing at EPRI. And I think the main reason we're here is that we're concerned about the future of SCMs in the U.S. and we rely on fly ash as a major source of SCM material to reduce our carbon footprint of concrete. Here's a projection from the Energy Information Administration. This is the U.S. government agency that tracks our energy use in all forms. So from transportation to industrial uses of energy to electricity, and they make projections about where we're headed. And this is their business as usual projection. It's actually the 2022, the most recent projection available. And right at the bottom, you can see on the base here for electricity, coal is a major source, a major fuel source of electricity in the US, but it's declining. And you can see since 2010, coal has been declining in generation, as we know, and it's forecast to continue to decline. This is the projection for business as usual. So on the right-hand side of the screen, you can see the CO2 associated with these projections, and this is the reference case we're looking at. So this reflects a sort of a stable amount of CO2 emissions, not much decline, not much growth. So when we think about what's happening in the bigger picture, we see carbon reduction goals on the forefront. At the federal government level, we've been talking about them over the last couple of years. So at the top left is a figure that EPRI's developed that shows if we were to achieve some of these substantial carbon reduction goals in the US, we'd have to have contributions from the electric sector and other sectors. So we can see electricity is in green on this figure, and we have to make a steep decline in the amount of CO2 associated with electricity to meet some of these aggressive goals, like having net zero by 2050 or reducing our emissions by 50% by 2030, those sort of goals. We also have to have contributions from industry and buildings. So that's in red. We see that we have to reduce the amount of CO2 there as well. So we know we've got this on the forefront. And what does that mean for coal-fired generation and our source of SCMs? If we're going to achieve these sorts of aggressive targets for CO2, we go from in the figure on the bottom right, we go from coal generation being a substantial part of our total electricity generated in a year to essentially nothing under a range of scenarios we've evaluated for different policy options that could achieve these sort of carbon reduction goals in the top left. So that's a really scary picture. By 2035, there could be very little coal generation, and as a consequence, very little fresh fly ash available. So what do we do to address that? Well, in the shortfall, in the short range, we can expand the use of off-specification products. So as Cole mentioned, bottom ash is rarely used as SCM. It has other uses. It can also be used for roofing shingles or as a media for blasting, for removing material, abrasive blasting. It has other uses, but we can put it to a better use, I think, through, as we're seeing, through use as a SCM. There are other SCMs available, spray dry absorber materials, that we won't talk about today. And then, as some of the other speakers mentioned, harvesting ash from existing impoundments and landfills. There's just tremendous resource, over 2 billion tons of CCPs in the US that could be put to use. And in particular, 560 ash ponds in the US are closing or will be closing soon. And in both of those, in landfills and especially in ash ponds, fly ash and bottom ash are often commingled. So it's not a matter of us deciding we want to use bottom ash. If we're going to tackle harvesting of materials, we're going to have to tackle bottom ash. I wanted to mention that some of the other speakers have talked briefly about where bottom ash comes from and kind of shown the diagram of a power station. But I wanted to just mention that there are a few different types of power stations. The predominant technology in the US is called pulverized coal combustion, and it's characterized by high combustion temperature and small coal particle size. The fuel that we're feeding to, it's a small size. And in that type of combustion, it tends to produce about 10 to 20% bottom ash and 80 to 90% fly ash. The design of those facilities, the boilers, they actually have two different types of designs, a dry bottom and a wet bottom. And that's important because in a dry bottom, the ash, the bottom ash falls to the bottom of the boiler and cools all in air. In a wet bottom boiler design, the ash particles fall out of the burning zone and they're partially cooled in air and partially cooled in water. So both of these, dry and wet, constitute the most common power station design. Another design that's somewhat similar to pulverized coal, but much less common in the US, is a cyclone boiler. So this is still a very high combustion temperature, but it's designed to produce bottom ash. So it takes a coal at a large particle size and ends up depositing almost all of it in the bottom of the boiler. The boiler designs on these are always a wet bottom where the ash particles are cooled or quenched in water. So just thinking about that, we've got this high temperature where we're melting the mineral material that's contained in the coal, but then we may be cooling it in air and maybe a little bit more slowly or maybe even faster in a wet bottom design. And then the third type I just want to mention that's not really very closely related to these two is fluidized bed combustion. And this occurs at a relatively lower combustion temperature and sort of a middle particle size, not as fine as pulverized coal, but not as coarse as cyclone combustion. This produces different type of ash entirely. Sometimes, unfortunately, we see people calling it bottom ash. A better name for the ash, the main ash that comes from fluidized bed combustion, is bed ash. So it has different characteristics, not only because of the design of the boiler, but the temperature that it operates at. And so I'd just be cautious if you're reviewing literature for someone else. If they mention fluidized bed, don't expect that to relate to what you might see with the ash we're used to seeing with pulverized coal combustion. And then when you're working if you're working on research projects, if you can find out what type of boiler and maybe the boiler design, whether it has a wet or dry bottom, that's valuable information because it may give us more insight into the applicability of the test results you're getting to the broader range of sources that are out there. And then I wanted to mention a little bit more about pulverized coal combustion. When coal's mined, it's crushed, and then at the power station, it's pulverized and classified before it's burned. And that's really important because it controls the particle size of the feed. So the typical specification for coal that goes into a utility boiler is 99% passing 300 microns and 70% passing 75 microns. So you can tell already this is really fine material. And when we think about bottom ash, we may think about particles that are maybe even larger than what we're putting into the boiler. So that should tell you immediately that what's happening in the boiler is not, we're not getting chunks of coal falling through the boiler. It's all burning up, and then the particles are agglomerating to get larger ash particles. So bottom ash isn't a waste material with things that didn't burn properly. It's a product of combustion and melting and fusion, just like fly ash is. It just maybe the particles have agglomerated differently than the particles that were carried up in the boiler. And just sort of as a reminder, the coals we use in the US, they tend to range from maybe 80 to 90% combustible material. So they tend to have this ash content of maybe 10 to 20% ash. And this on the right is a kind of exploded diagram of the pulverizers that we use in coal-fired power stations. So the coal, the fuel falls down through the center and it's ground on these grinding wheels, and primary air that's heated carries the small particles of coal back up through the classification and to the combustion process. So there are people at a power station that pay attention to the operation of this equipment day in and day out when it's running, because it's how the process is made to be reliable and consistent. And then we've seen the diagrams, the sketches of what a boiler looks like, but I wanted to just include some pictures so you have an idea. At the very bottom of a boiler, there are a couple pictures on the left-hand side of the bottoms of boilers. This is where bottom ash is cooling down and being collected and sent away. And then sort of an exploded diagram of one type of bottom for a boiler that shows that there is already a crushing step that usually happens at the power station. And then on the right, there's a picture of a pile of bottom ash. This is from a dewatering system. It turns out that recently in the past, we almost always sluiced bottom ash. That is, it was transported wet to wherever it was going. Recently, we've had some power stations install dry handling. So they can have a boiler that has no water at the bottom of it at all, and the ash is just conveyed dry to a storage area or dry to processing. And so that's the ash we're going to talk about. I wanted to focus on one particular ash that we did some testing, and you actually heard about it in an earlier presentation, but I'll try and tackle it from a different direction a little bit. So this is from a 2.9 gigawatt power station. That's pretty big, but not the biggest. They burn a subbituminous fuel, Powder River Basin. So that should produce a Class C kind of ash. The composition is pretty well understood to produce that. This station has 4 subcritical boilers that are about 7 megawatts capacity each. And it's got a dry bottom design with dry ash handling. So there's no water at the bottom of the boiler to quench the ash or transport it away. The composition you can kind of see here. The important thing to note is about 21% calcium oxide content, really low LOI. And there's a picture of a bucket sample of the material we were testing. So what I'm going to talk about are some results from a project we did with Oregon State, and one of the presenters already talked about these results, so I'll go through them kind of quickly. In this project, we used a commercial tolling company to grind bottom ash, and they targeted a 50% diameter of 19 microns, or actually 20 microns. They undershot it a little bit. We were shooting to make about the same 50th percentile as we think of fly ash, which is about 20 microns, 50th percentile. So the PI was Dr. Iskor, who I don't know if he's still here or not, and some other folks. So you can ask them all the tough questions. I'll just show you some pretty pictures that they made for us. So this was the project where we talked about performance mix design and using thermodynamic modeling and pore partition modeling to arrive at a concrete mix design. And I think you may have already seen this diagram. In the previous presentation, they just focused on one of the concrete mixtures, but the Oregon State team actually made three different concrete mixtures targeted to different applications. So these are on the left-hand side. You can see the performance criteria that they developed. This was what we were setting out to meet. And then they developed a mix design with this Ash 3, which was from that power station I just talked about, the dry bottom with the dry handling and the commercial milling to 19 microns average particle size. So three different concrete mix designs that that were actually made. And these are the characteristics of the mixes as they were made. And this is where they were targeting in their modeling, targeting one mix outside of the performance feasibility space in their models. So the idea was to check to see that they weren't, under predicting the performance. If we could get it outside of the model, then that would tell us that we knew where this boundary was from the outside, and then a couple on the inside of the feasibility space. And they were successful. So this has got, I apologize, these figures have got results from several different coal combustion products, but what we want to focus on is the yellow bars for ash 3. That's the ground bottom ash. And we met in terms of strength. We met all the strength that we had anticipated. We met the apparent formation factor, except for bottom ash 3, and that was intentional. That was where we were outside of the feasible space. We also met our pH and our calcium hydroxide content. So the reason why I wanted to run through this is it showed we could make concrete with bottom ash that met all of our performance criteria. So I thought that was in addition to learning about the modeling and using the modeling, I thought just showing that we could make the concrete meet performance criteria was valuable for the audience and for this session. And then I want to mention a research project that I happened to see a presentation on at the end of last year. Dr. Bosniak from University of Stuttgart presented on ground bottom ash as a STM, focusing on materials, bottom ash materials from Germany. I thought this was interesting. We're not alone here in the US. It's not US and Canada. A lot of people are interested in ground bottom ash. I think there was also a presentation from some folks working in Malaysia on this issue. So yeah, I think worldwide appeal to it. They did a good range of testing, but what I want to focus on is mortar strength results, a strength activity kind of test using ground bottom ash at 4 different finenesses. And the way they express this is less than 10% retained on 45 microns, so pretty aggressive grinding, making it very fine, and then all the way up to bottom ash ground to between 40 and 45% retained on the 45 micron sieve. So that would be something that wouldn't pass C618 criteria. It'd be too coarse. And they tested this at three different cement replacement levels, 10, 20, 30%, and they evaluated mortar strength all the way out to 90 days. They met the mortar strength requirements, so the percentage of their control. And by the time they got to 90 days, all 4 of these bottom ashes, even the coarse bottom ash, exceeded the control strength activity or strength. So it was very successful. Seemed to be contributing to strength at the long term. And what made me somewhat interested is at 30% replacement, when we looked at the 90% or 90-day mortar strength results, there was a notable decline in the strength between the very finely ground ash and the coarse ash. So all of them exceeded the reference, but the fine did perform well. So I wanted to go back and think about the value of grinding at different sizes. And I happened to be talking with Dr. Ma at Missouri S&T, my alma mater, and thinking about this problem. And so he's been working on some research, and I want to present some of the preliminary results, just thinking about grinding and particle size on this one particular ash that we already made concrete with. So we started with ash, and on the right-hand side of the figure, you can see the raw ash particle size distribution by sieving to give you an idea where we started. And then we ground it for a number of different, at a number of different trials for different lengths of time. And you can see 3 particle size distributions. That reflects 2 minutes of grinding, 5 minutes, and 20 minutes. And this isn't the commercial grinding that we did for the previous study with Oregon State. This is just in a lab. So these numbers, they don't really relate to a particular commercial piece of equipment. It could be that this lab grinding is more aggressive than it'd be more aggressive than the ball mill that Cole used, for example. This is a disc, vibratory disc grinder. So it'd be more aggressive than the ball mill, for example, but it doesn't, directly relate to a commercial piece of grinding equipment. But nonetheless, we know that something ground for 20 minutes used more energy than something ground for 2 minutes. Which was what I was trying to understand. And then on the right, you can see just the relationship between D50, the median particle size, and grinding time. So there was a really substantial drop off in the effectiveness of the grinding after about 2 minutes. So that might be another way you might determine how much grinding you do, rather than having a fineness requirement. Maybe you're grinding it until it's not worth the effort, or you certainly hope you don't have to go out here where it's less effective. And then the relationship that we have results for and we can look at is with the isothermal calorimeter results for using ASTM 1897, the R3 method. You can see the material ground to 10 microns. That took 20 minutes of grinding. It has more reactivity at seven days of reaction than the 16 micron or the 10 or the 20 micron. Whether or not it's worth it to grind it that much more, I don't know. We don't have a strength relationship here yet. And we're running some other testing, and I wanted to share those results too. We have a bottom ash and a fly ash mixture. This is not a harvested ash, but it came from the power station this way. And that started out really with a pretty low reactivity, and with just a little bit of grinding, the reactivity dramatically increased. And similarly with the harvested bottom ash fine. So this was from a ash pond closure project where the ash was going through a hydrocyclone, and we took the underflow and then we sieved out the finer material. And so what we retained was what we believe was mainly bottom ash. And again, this one had a pretty substantial increase in reactivity when we ground it. And both of these were low calcium ash, so not really directly relatable to the high calcium ash, where we didn't see nearly the increase in reactivity. And then I just wanted to make one more thought about when we were looking at the grinding. Here are some SEM pictures, sort of on the left. You can see the least amount of grinding, and then on the right, as you'd expect, finer particles after more grinding. The numbers on the figures represent an image analysis to give us an idea about the roundness. So the top row here is the high calcium ash that was dry bottom power station, dry conveyance. We seem to, at least with this image analysis, we seem to reduce the angularity by doing the grinding. So maybe that's a bit of a positive as well that we could think about. The mixture of fly ash and bottom ash, which was actually a little bit, I think, heavy on fly ash, we actually increased the angularity of that. So maybe we don't want to grind fly ash necessarily. And then the mostly bottom ash mixture harvested from an ash pond, we think we increased the reduced angularity of that material. Yeah, thank you. So with that, I just wanted to make a few conclusions. If you can get information about the power station where you're getting ash samples, that's really useful for some of us to hear, so we can relate it to other power stations and make predictions about an ash at a different location. I think evidence shows you can make concrete with bottom ash, make successful concrete that achieves strength and is durable. And then, as you'd expect, grinding seems to increase reactivity.